Just an off-the-cuff video to go over something that I found kind of useful. Maybe I don't even know what the name of the technique would be, but maybe this would be useful to someone else out there, or maybe I'll just remember this in the future and be able to come back to this video. So here's a little project. Here's a little problem I'm working on. I'm working on an interrupt vector table implementation. I'm seeing that there's some bugs with it. So one of the things that I would do is relocate the interrupt vector table from Flash over to RAM, create like a static buffer for it. And what I would actually do is I put a whole bunch of no-op functions inside of it. No-op functions basically just placeholders for now. I'm probably going to make them actually call the hard fault handler or another handler, so we can get that information about which particular vector was called in the appropriate way. But one thing I was noticing is that as far as I could tell, the active vector that was running didn't seem to correspond to the entries inside the interrupt vector table, which was weird to me. So I set out to see which one of the items inside the vector table were running. And the problem I was having before is that if I only put no-op here, all I know is that I jumped into the no-op function and got stuck there. I didn't know which no-op got called. So I came up with a clever idea. So I'm just going to comment this out. I created this little fill function. So before I was using the standard algorithm fill in order to fill this vector with a whole bunch of no-op functions. The no-op function looked similar to this up here, just without the template parameter. Okay, and they would just go in there and loop and be stuck. Now what I did next was I decided to create this thing called the fill function, my little local fill function. What it will do is it'll take an array, it'll take the length of the array, and it'll take an index, so you usually just give it 0, or you don't give it anything. It'll default initialize the first template parameter. And the idea here is I want to annotate every single one of the no-op functions. So rather than having just one singular no-op function that all of them point to, have a new no-op function for each entry inside the table. So the way I did this at compile time, because it's a template, and you can't just instantiate new templates like you do in a normal for loop. You can't just do this. You can't do for int I is equal to 0, I is less than, I'm just going to say vector buffer dot size I plus plus. That doesn't work because I is a runtime variable, so I couldn't do this. This is not going to work. And there's no constexpr for, although I think they might be making one at some point. I think that might be in the future. It'd be really cool. This actually would make this thing a lot easier. So I needed some way to do this at compile time. So what I actually did was I made this thing recursive, the fill function. Zoom in a little bit, get rid of all of this. The fill function takes in the array. It is able to deduce its length. You give it an index, defaults at 0. Maybe you want to do a further up index, I'm not sure. And we utilize C++ 17s. If const expression, it might be also C++ 20s. Forget which one it is. And what we're just doing is we're checking to see if the index is less than length, kind of like what you normally do in a for loop conditional. And we say table index, so starting at 0, is equal to no-op index. Because this is a compile time value, you can just throw this right into the template argument. And now you have no-op 0 for the first run of this. Then what we do is we run fill again, but we increment index plus 1. So this is recursive. We go down and we pass the table again. So we roll back up. This is now 1. 1 is less than, in this case, I think like length would be like 59 or 30 or whatever. Then we put table index 1 is equal to no-op version 1 or template value 1. Then we do fill index plus 1, and we keep incrementing until eventually we get to the top. We get to the end. Then the fill has no more recursive calls. It rolls back up all the way to the top. This all happens at compile time. Or the code generation, the codegen will generate code that does this at compile time, generating all the different versions of no-op. So then every time you run this little initialize function that sets up your vector table and throws it into, relocates the vector address for ARM, this thing will now be filled. Now this is a debug thing. You wouldn't want to do this in production because, well, in production, you don't want to have a whole bunch of arbitrary functions. I'm not sure what the exact size would be, but it'd at least be a good couple of bytes per each one. And, I don't think that's really necessary. I think having a better handler versus just a no-op function would be better. That actually describes to you what's happening. Although even when I started looking at the different registers, it didn't seem to give me enough information about which vector was being run. So that's kind of the technique. The cool thing about this is that because it annotates which, each function is completely different, you can actually see inside its signature. So if I zoom up, we have a, using GDB dashboard. I'm in GDB right now. And you can actually see that if I look at where I'm at, I triggered one of my interrupts, And you can see that from here, I'm in no-op 22. Now I expected myself to be in no-op 54, or to be in to have executed from index 54, but I indexed at 22, which doesn't make any sense. I haven't figured out this problem yet, but this at least gives me a really strong clue as to what's going wrong. I know that, this gives me a really strong view of what's going wrong here. So I can use this in order to better solve my problem. So that's all I wanted to talk about today, is the way to annotate kind of default functions where you have a whole bunch of them and trying to give them some unique value at compile time so you can figure out what's going on at runtime. And then once you figure that out, you can actually eliminate all this stuff and then revert your code back. Maybe even add a debug flag or something along those lines so that you can add this back in if you would like to when you debug stuff. So that is pretty much the little technique that I have here. I have no idea what to call this, but I thought it'd be cool to share. All right, talk to you guys later.